Welcome to Midnight Explorations, a quiet place for gentle journeys and deep rest. Tonight, we descend into the depths of the earth, following the clues that fire and stone have left on the surface, tracing the slow work of geologists and observers who sought to understand the heat that moves beneath our feet. These are stories of volcanoes and minerals, of patient watching and gradual understanding, of a planet that remains alive with hidden warmth long after its surface has cooled. For the next little while, there's nothing for you to do and nowhere for you to go. Let the day fade into the distance and focus on getting comfortable and breathing deeply. There is no urgency here, only the slow rhythm of geological time, the patient accumulation of observations that eventually revealed what lies beneath. Let these stories carry you gently through the night as we explore the hidden depths together. Close your eyes now and let go. The depths of the earth are hidden from us. We walk on solid ground surrounded by familiar landscapes, and the rock beneath our feet seems as permanent and unchanging as anything can be. But there are places where the planet reveals something of its interior, where heat and light and molten stone rise to the surface and remind us that the ground we stand on is only a thin shell over something vast and hot and still in motion. Volcanoes have always been the most visible of these revelations, a mountain that sends fire and ash into the sky, that pours rivers of glowing rock down its slopes, that shakes the ground and fills the air with smoke and thunder, would naturally draw attention and invite explanation. The earliest human observers of volcanoes had no way to understand what they were seeing in terms we would recognize as scientific. But they watched, and they wondered, and they recorded what they saw in paintings and stories, and eventually in written accounts that would survive for centuries. Hot springs offered gentler evidence of the same hidden heat. Water that emerged from the ground already warm, sometimes hot enough to scald, sometimes bubbling with gases that smelled of sulfur and other strange substances. These springs spoke of warmth below, of processes happening in darkness that the surface only hinted at. People learned to use these springs for bathing and healing, for cooking and warmth, without understanding where the heat came from. The practical knowledge preceded the theoretical by thousands of years. The glowing of lava, whether flowing from a volcanic vent or exposed where the Earth's crust had cracked, offered the most direct evidence that something molten existed below. The rock that seemed so solid could become liquid, could flow like water, though much more slowly, could cool and harden into new forms that bore the marks of their fiery origin. This transformation from solid to liquid and back again was a kind of clue, a hint that the permanence of stone was not absolute, that given enough heat, even the hardest rock could be made to flow. These surface signs were all that ancient observers had to work with. They could not drill into the earth, could not send instruments into the depths, could not see directly what lay below. Everything they understood about the interior had to be drawn from what appeared at the surface, from the behavior of volcanoes and hot springs, from the rocks that eruptions brought up from below. The depths remained hidden, but they were not silent. They spoke through fire and heat, through rumbling and shaking, through the strange substances that rose from below. Learning to read these signs would take centuries of patient observation. And you remain here, settled and still, while the long story of that watching unfolds around you. The earliest human records of volcanic activity are difficult to interpret with certainty. A wall painting discovered at Çatalhöyük, in what is now Turkey, dates to approximately 7,000 years before the Common Era and appears to show a settlement beneath a twin-peaked mountain. from which something rises. Perhaps smoke, perhaps an eruption plume. If this interpretation is correct, it represents one of the earliest visual records of human awareness of volcanic activity. A moment held in pigment when someone looked at a fiery mountain and thought it worth depicting. The uncertainty about the Çatalhöyük painting is part of what it has to tell us. We cannot be certain what the ancient artist intended to show, whether the rising forms represent an eruption or something else entirely. The painting survives, but the context that would allow us to understand it fully does not. The observations were made, but the frameworks for interpreting them were different from ours, and the connections between image and meaning are not always clear. The written records of the ancient Mediterranean world offer more detailed accounts, though they too require careful interpretation. Greek and Roman writers described the volcanoes they knew, Mount Etna in Sicily and Vesuvius in Italy, with a mixture of observation and mythological explanation. They noted the fire that emerged from the mountains, the smoke that rose from their peaks, the rumbling that sometimes preceded eruptions. They also attributed these phenomena to divine causes, to the forges of Hephaestus or Vulcan, to giants imprisoned beneath the mountains, to punishments inflicted by the gods. This combination of observation and myth was less a failure of intelligence than a reflection of the frameworks available for understanding. The ancient observers saw accurately. Their descriptions of volcanic phenomena are often remarkably detailed and correspond well to what modern observers see. But they did not yet have the concepts that would allow them to explain what they saw in terms of geological processes. The gods and giants offered explanations that made sense within the cultural context, that answered the questions of why and how in terms the audience could understand. Mount Etna, rising on the eastern coast of Sicily, was particularly prominent in ancient accounts. Its frequent activity made it a natural subject for observation and speculation. Writers noted the flows of lava that descended its slopes, the changes in the shape of its summit crater, the periods of quiet and the periods of violent eruption. The mountain was a constant presence, visible from great distances, its plumes of smoke and occasional eruptions reminders of the fire that burned within. The interpretation of these phenomena as the work of divine smiths or imprisoned giants served purposes beyond mere explanation. The stories connected the natural world to the world of meaning and value, made the volcanoes part of narratives that helped people understand their place in the cosmos. The giant Typhon, said to be buried beneath Etna, was a figure of chaos and destruction. His imprisonment carried a sense of order holding sway over disorder, a reassurance that the terrifying power of the volcano was contained, held in check by forces greater than itself. The experience of standing near an active volcano is unlike anything else the natural world offers. The ground itself may tremble, a constant low vibration that seems to rise from the depths. The air smells of sulfur and other gases, an acrid presence that catches in the throat and stings the eyes. The sound is not what one might expect from descriptions of eruptions. Between the dramatic explosions, there is often a continuous roar, like a distant furnace, or a deep rumbling that seems to come from everywhere at once. The heat radiates outward, palpable even at a distance, a reminder that what seems like solid rock is in fact a thin barrier between the surface world and something molten below. Those who have climbed active volcanoes describe a landscape that seems barely stable, as if the ground might at any moment open beneath their feet. Cracks in the rock release wisps of steam and gas, marking pathways where heat escapes from the interior. The rocks themselves are often warm to the touch, sometimes too hot to hold for more than a moment. The colors are strange: yellows and oranges from sulfur deposits, reds and blacks from oxidized iron, the blue shimmer of burning gases. It is a landscape that does not belong to the ordinary world, a glimpse of something usually hidden. The people who live near active volcanoes have developed their own relationships with these dangerous neighbors. They know the signs that precede eruptions, passed down through generations of observation. They know which areas are safe and which are not, where the pyroclastic flows will travel and where they can be avoided. This local knowledge, accumulated over centuries, often proves as valuable as scientific monitoring, a practical wisdom born of long coexistence with forces that cannot be controlled, but can sometimes be anticipated. The stillness around you continues, while these distant mountains and their distant observers move slowly through their stories. The eruption of Vesuvius in 79 CE produced one of the most detailed written accounts of volcanic catastrophe to survive from the ancient world. The letters of Pliny the Younger, written some years after the event to the historian Tacitus, describe what he witnessed as a young man and what he learned from survivors about the destruction of Pompeii and Herculaneum. These letters became foundational documents in the history of volcanology, so influential in fact that the type of eruption they describe, a towering column of ash and gas that collapses into devastating pyroclastic flows, is still called a Plinian eruption. Pliny was staying with his uncle, Pliny the Elder, at Misenum, across the Bay of Naples from Vesuvius, when the eruption began. His account describes the appearance of a cloud rising from the mountain, shaped like a pine tree, with a tall trunk and spreading branches, its color varying from white to dark, depending on whether it carried more ash or more earth. This description of the eruption column is remarkably accurate. It captures the essential features of what modern volcanologists call a Plinian column: the vertical rise, the spreading at altitude as the column loses its momentum, the variations in color and density. The elder Pliny, a natural philosopher and naval commander, set out across the bay to investigate the phenomenon and to rescue friends who were trapped near the volcano. His nephew remained behind and watched from a distance as darkness fell over the region, as earthquakes shook the buildings, as ash began to fall even at Misenum, miles from the eruption. The uncle died during the rescue attempt, apparently from inhaling volcanic gases, becoming one of the many lost in the disaster. The younger Pliny's letters describe the sensory experience of the eruption with striking clarity. The darkness that fell during the day, thicker than any ordinary night, broken only by flames from various sources. The earthquakes that rocked the buildings, making it dangerous to stay indoors, but equally dangerous to venture outside where falling debris threatened. The rain of pumice and ash that accumulated on roofs and in streets, forcing people to shake it off periodically to avoid being buried. The unease of the population, some leaving by land, some by sea, some simply waiting in their homes for whatever would come. The burial of Pompeii and Herculaneum preserved those cities in a state that would not be matched until modern archaeology developed the techniques to excavate them. The ash that fell on the inhabitants also protected the buildings, the streets, the objects of daily life, even the shapes of the people themselves, held in their final moments by the material that enclosed them. When excavation began, centuries later, the cities emerged as time capsules, windows into Roman life that no other source could provide. The preservation was also a form of documentation. The layers of volcanic material that buried the cities recorded the sequence of the eruption, the different phases of ashfall and pyroclastic flow, the times and intensities of the various events. Modern volcanologists have studied these deposits carefully, slowly reconstructing the eruption in detail, coming to understand not just what happened, but how it happened. The sequence of events that turned a mountain into something unsurvivable. The same deposits that ended so many lives also held evidence that would eventually help protect others. The transition from observation to systematic study was gradual, stretching across centuries. The medieval period in Europe saw relatively little advance in understanding volcanoes, though eruptions continued to be observed and recorded when they occurred. The focus of intellectual life lay elsewhere, and the frameworks for understanding the natural world emphasized divine providence and scriptural authority over empirical investigation. Volcanoes were wonders to be marveled at, signs to be interpreted, but not yet phenomena to be explained through natural causes alone. The 16th century brought renewed interest in careful observation of the natural world. Scholars and miners in various parts of Europe began to collect more systematic notes on rocks, minerals, and volcanic landscapes. Mining, in particular, drew interest in what lay beneath the surface. The search for valuable ores called for understanding of how rock formations were arranged, where different minerals could be found, how the earth was structured at least in its upper layers. This practical knowledge accumulated gradually, forming a foundation for later theoretical developments. The contributions of Nicholas Steno in the 17th century moved understanding of volcanic rocks a little further along. Steno, a Danish anatomist working in Italy, laid out principles of rock layering that would become fundamental to geology. He recognized that sedimentary rocks were formed from particles settling in water, that the layers were originally horizontal, that older layers lay beneath younger ones. He also recognized that some rocks had a different origin, that they were formed from molten material that had cooled and solidified. This recognition gently connected volcanic lava to the broader structure of the crust, drawing surface observations toward deeper processes. Steno's work was notable for its clarity and its reliance on careful observation rather than inherited authority. He looked at rocks and reasoned from what he saw, drawing conclusions that could be tested against other observations. This approach would become the foundation of modern geology, though it would take another century and more before the field fully developed. The principles Steno articulated in 1669 remain valid today, foundational elements of how geologists understand the Earth. Slowly, the recognition that volcanic rocks were solidified from molten material opened new questions. Where did the molten material come from? How deep did it originate? What kept it hot enough to remain liquid? These questions could not be answered with the tools available in the 17th century, but they could be formulated, and their formulation was itself a quiet kind of progress. Understanding tends to begin with such questions, and Steno and his contemporaries were beginning to ask the ones that would, in time, lead toward an understanding of the Earth's interior. The space around you stays unchanged, while these slow movements of thought drift past, century into century. The burial of Pompeii had created a time capsule that would not be opened for nearly 17 centuries. The ash that fell on the city's inhabitants also preserved it, sealing buildings and streets, objects and bodies, in a matrix that protected them from decay and disturbance. When excavation began in the 18th century, archaeologists found a Roman city essentially complete, its architecture intact, its artifacts in place, its people held in their final moments. The preservation extended to details that would otherwise have been lost entirely. Organic materials that normally decay, wood and food and textiles, were carbonized by the heat or preserved by the lack of oxygen beneath the ash. Graffiti on walls, painted signs for shops and taverns, everyday inscriptions that would never have been considered worth preserving, survived because everything survived. The city that emerged from excavation was not a collection of monuments and treasures, but a complete environment, a place where ordinary life had been lived and could now be studied. The human remains at Pompeii are particularly affecting. The ash that settled around people formed molds around their bodies, and when the bodies decayed, the molds remained. By pouring plaster into these cavities, archaeologists could create casts that showed the forms of the victims in their final moments, their postures and gestures preserved, their experience made visible across 2 millennia. These casts are among the most quietly moving artifacts ever recovered, a reminder that the volcanic event was not an abstract geological occurrence, but something that had touched individual lives. The pyroclastic flows that swept through Pompeii and Herculaneum remain among the most intense of volcanic phenomena. These fast-moving clouds of hot gas, ash, and rock fragments can travel at speeds exceeding 100 kilometers per hour, far too fast for anyone in their path to escape. Their temperatures can exceed several hundred degrees Celsius, hot enough to bring death almost instantly through thermal shock. The combination of speed, heat, and the suspended solid particles makes pyroclastic flows almost invariably fatal to anyone caught in their path. The formation of pyroclastic flows occurs when the column of ash and gas rising from a volcanic vent becomes too dense to continue rising and collapses back onto the volcano's flanks. The collapsing material, still hot and charged with gas, becomes a ground-hugging flow that descends the slopes, following valleys and depressions in the terrain. The flow may travel many kilometers from its source, depending on its volume and the topography it encounters. It can reach areas that seem safe from the eruption itself. The protection of populations from pyroclastic flows depends primarily on evacuation before they occur. Once a flow is underway, there is no safe refuge within its path. The only protection is distance. Volcano monitoring aims to provide warning of eruptions likely to produce pyroclastic flows, allowing authorities to move populations away before the flows descend. The success of such evacuations depends on accurate forecasting, effective communication, and the willingness of populations to leave their homes on the basis of warnings that might, in the end, prove unnecessary. The letter writing that characterized 18th century scientific communication created networks of knowledge that spanned continents. A naturalist in Naples could correspond with colleagues in London, Paris, and Stockholm, sharing observations that would otherwise remain local and unknown. The Royal Society of London, to which Hamilton sent his reports, served as a clearinghouse for such communications, receiving letters from observers around the world and publishing those of sufficient interest in its philosophical transactions. This system of correspondence had limitations, but also strengths. The time required for letters to travel meant that information moved slowly, weeks or months passing between observation and publication. But the requirement to write out observations in detail brought a certain clarity of description, a discipline of expression that casual conversation would not have demanded. The letters that survive from this period are often remarkably thorough, their authors understanding that their distant readers would need context and detail that might be assumed in face-to-face communication. Hamilton's letters to the Royal Society show this tradition at its most patient. He wrote not for immediate response, but for the record, knowing that his observations would be preserved and consulted by future readers. He took care to distinguish between what he had seen himself and what he had learned from others, between certain observation and tentative interpretation. The scientific caution that characterizes good research was present in his writing, even as his enthusiasm for his subject was evident on every page. In 1764, Sir William Hamilton arrived in Naples as British envoy to the Kingdom of the Two Sicilies. He would remain in Italy for decades, and during that time, he would gradually grow from a diplomat with an amateur interest in natural phenomena into one of the most important early students of volcanic activity. His residence near Vesuvius gave him opportunities for observation that few others enjoyed, and he pursued those opportunities with dedication and care. Hamilton was drawn to Vesuvius from his first encounters with the mountain. Unlike visitors who came, observed an eruption, and left, Hamilton stayed. He climbed the volcano repeatedly, during periods of quiet and periods of activity, in daylight and darkness, in good weather and bad. He watched the changes in the crater, the variations in the smoke and steam that rose from it, the flows of lava that occasionally descended its flanks. He became intimately familiar with the mountain's moods and patterns in a way that no casual visitor could. Between 1764 and 1767, Vesuvius entered a multi-year phase of heightened activity. Hamilton was there to observe it, climbing the mountain sometimes daily to watch the changes, recording what he saw in letters that he sent to the Royal Society in London. These letters were not casual correspondence, but careful scientific reports, detailed descriptions of phenomena that Hamilton knew would be of interest to the learned community. He described the appearance of lava, its color and consistency, the way it moved and cooled. He described the sounds of eruptions, the rumbling and explosions, the hissing of steam. He described the smells, the sulfurous gases that rose from vents and made breathing difficult near the crater. The Royal Society published Hamilton's letters, making his observations available to a wider audience. In 1772, his accumulated observations were read to the Society, establishing his reputation as a serious student of volcanic phenomena. His approach was methodical and patient, emphasizing repeated observation over time rather than dramatic single encounters. He understood that volcanoes were not static objects, but dynamic systems, that understanding them required watching them change over weeks and months and years. Hamilton's dedication to observation was remarkable for its persistence. He continued climbing Vesuvius well into his 60s, an age when such exertion was neither expected nor advisable. He was guided by genuine curiosity, a wish to understand what he was seeing, to add something lasting to human knowledge of volcanic processes. His work showed that scientific study of volcanoes was possible, that patient observation could yield understanding, that the powerful phenomena of eruptions could be approached with calm and method. The relationships Hamilton developed with local guides and inhabitants proved valuable. The people who lived on and around Vesuvius had their own knowledge of the mountain. Practical understanding accumulated over generations. They knew the signs that preceded eruptions, the safe paths for climbing, the hazards to avoid. Hamilton learned from them even as he observed for himself, combining local knowledge with his own systematic approach. The collaboration between foreign observer and local expert would become a pattern in volcanic studies, repeated at volcanoes around the world. In 1776, Hamilton published Campi Flegrae, a work that would set a new standard for volcanic documentation. The title referred to the volcanic region around Naples, the fields of fire that included Vesuvius, but also numerous other volcanic features, craters, hot springs, areas of ongoing geothermal activity. The work combined Hamilton's written observations with a series of hand-colored engravings that depicted volcanic phenomena with unprecedented accuracy and detail. The engravings in Campi Flegraei were the work of Pietro Fabris, an artist Hamilton commissioned to accompany him on his volcanic expeditions. Fabris painted what he saw: the colors of lava flows at different temperatures, the shapes of eruption plumes, the forms of craters before and after eruptions. The paintings were then translated into engravings by skilled craftsmen, a process that required interpreting the original colors and tones in terms of lines and hatching. Finally, each printed engraving was colored by hand, using the original painting as a guide, recreating the colors that the printing process could not reproduce. The publication of these images carried weight for several reasons. It allowed people who would never visit Naples to see what volcanic activity looked like, to understand through visual representation what written descriptions could only approximate. It created a record that could be compared to later observations, allowing changes to be documented over time. And it established a standard for scientific illustration that would influence later works, suggesting that careful visual documentation was an essential part of volcanic study. Across these images, eruptions appeared in progress, columns of fire and ash rising from Vesuvius, lava flowing down slopes, the glow of molten rock against the darkness of night. They showed the crater in various states, smoking quietly or filled with active lava. They showed the broader landscape, the relationship between the volcano and the surrounding countryside, the towns that sat in the shadow of the mountain. The comprehensive visual record provided context that individual observations lacked. In 1779, Hamilton published a supplement to Campi Flegraei, documenting another major eruption of Vesuvius that had occurred after the original publication. This supplement continued the approach of combining written description with detailed illustration, adding new images of lava fountains and ash clouds of the mountain during and after the eruption. The willingness to update and extend the original work reflected Hamilton's commitment to ongoing observation, his understanding that volcanic study was not a project with a defined end, but a continuing engagement with a changing subject. The influence of Campi Flegraei extended beyond its immediate readership. It established conventions for depicting volcanic phenomena that would be followed by later observers. It showed that scientific and artistic approaches could be combined productively, that accurate illustration was not opposed to aesthetic quality, but could enhance it. And it made Hamilton's observations accessible to a wider audience than his Royal Society letters had reached, contributing to growing public interest in geological phenomena. The production of the engravings for Campi Flegraei was itself a significant undertaking. Each image began as a painting by Pietro Fabris, created on site during volcanic activity or based on detailed sketches made during expeditions. The paintings were then translated into engravings by skilled craftsmen, a process that required interpreting the original colors and tones in terms of lines and hatching. Finally, each printed engraving was colored by hand, using the original painting as a guide, recreating the colors that the printing process could not reproduce. The hand coloring of prints was a common practice in the 18th century for works that required accurate color representation. Each copy of the book required its own coloring, making the production labor-intensive and the resulting volumes expensive. The colors were applied by teams of colorists, often women, who worked from sample copies to ensure consistency across the edition. The skill required was considerable. The colors had to match the originals closely enough that the scientific value of the images was preserved. The result was a publication of unusual beauty as well as scientific value. The images of erupting Vesuvius, of lava flowing down the mountain's flanks, of the interior of the crater with its pools of molten rock, were unlike anything that had been published before. They brought the experience of volcanic observation to readers who would never climb Vesuvius themselves, allowing them to see what Hamilton had seen, to come closer in visual terms to what words alone could not convey. The conversation between Neptunus and Plutonus in the late 18th and early 19th centuries shows how scientific understanding of the Earth's interior developed through gradual exchange and eventual settlement. The Neptunus, following the German geologist Abraham Gottlob Werner, believed that all rocks had precipitated from a universal ocean, that even volcanic rocks like basalt were sedimentary in origin. The Plutonus, influenced by the Scottish geologist James Hutton, held that many rocks had crystallized from molten material, that the Earth's interior was hot, and that this heat was responsible for volcanic activity. The evidence eventually came to favor the Plutonus. Field observations showed that basalt could be traced to volcanic sources, that the same rock type found in ancient formations was still being produced by active volcanoes. Experimental work showed that rocks could be melted, and that the resulting material, when cooled, resembled volcanic rocks in texture and composition. The identification of contact metamorphism, the alteration of rocks adjacent to volcanic intrusions by heat, added further evidence that molten material had been present at depth. The settling of this debate carried weight for more than just the question of rock origins. If volcanic rocks came from melted material deep within the Earth, then the Earth must contain significant internal heat. This heat could lie behind not only volcanic eruptions, but other geological processes as well, mountain building and metamorphism, and the movements of continents that would not be understood until much later. The recognition that the Earth was internally hot quietly opened new avenues of inquiry that would occupy geologists for generations. The observations of Hamilton and others gradually opened questions that called for theoretical explanation. If lava was molten rock that rose from below, what was the source of the heat that melted it? If volcanoes brought material from the Earth's interior to the surface, what was that interior like? The 18th and 19th centuries saw the slow development of ideas about Earth's internal structure. Ideas that would eventually draw the scattered observations of volcanic activity into a coherent picture of planetary processes. The recognition that volcanic rocks were solidified forms of once molten material was a quiet but important step. Geologists learned to identify different types of volcanic rock: basalt, dark and dense, common in lava flows; andesite, intermediate in composition, typical of explosive volcanoes; rhyolite, light-colored and rich in silica, associated with the most violent eruptions. These different rock types told of different conditions of melting and cooling, different compositions in the source regions, different paths to the surface. Gradually, it came to be understood that the Earth was hot inside, that beneath the solid crust on which we live lay hotter layers, regions where rock could be soft or even molten under the right conditions. This internal heat was not evenly distributed. It concentrated in certain places, rising toward the surface through mechanisms that were not yet understood. Where it rose, volcanoes formed, bringing samples of the deep interior to the surface where they could be studied. The connection between surface lava and deep heat was not immediately obvious. Some early theories proposed that volcanic heat came from chemical reactions near the surface, from burning coal deposits, or from the reaction of water with certain minerals. These theories explain some observations, but not others. Why were volcanoes distributed as they were? Why did some regions have many volcanoes while others had none? The chemical theories could not answer these questions, suggesting that the true explanation lay elsewhere. The thermal theories that eventually settled into place proposed that the Earth retained heat from its formation, that the interior was hot because it had not yet cooled from an originally molten state. This heat rose slowly toward the surface, occasionally breaking through in volcanic eruptions, constantly influencing the behavior of rocks at depth. The Earth was not a cold, dead body, but an active one, moved by internal heat that expressed itself in volcanoes, earthquakes, and the slow shifting of continents that would not be understood until much later. Steadily, these ideas drew together, with contributions from many observers and thinkers. No single discovery established the theory of Earth's internal heat. Rather, the accumulation of evidence from many sources gradually made the idea seem natural. The volcanic rocks themselves, the distribution of hot springs, the temperatures measured in deep mines, the behavior of volcanoes over time. All of these pointed toward a hot interior, a source of energy that lay behind the geological processes visible at the surface. And the stillness continues, while the slow accumulation of these ideas drifts on. The establishment of permanent volcano observatories marked a new phase in the study of Earth's depths. Rather than visiting volcanoes only during dramatic eruptions, scientists began to watch them continuously, maintaining presence through periods of quiet as well as periods of activity. This continuous observation revealed patterns that intermittent visits could not detect, subtle changes that preceded eruptions, cycles, and rhythms in volcanic behavior. The Vesuvius Observatory, established in 1841, was among the earliest dedicated facilities for volcanic monitoring. Positioned on the slopes of the mountain that had fascinated Hamilton and so many others, the observatory maintained instruments and staff to watch the volcano through all its phases. The choice of Vesuvius was natural. The mountain was accessible, active, and already well known from centuries of observation. It offered an ideal subject for the new approach of systematic, continuous monitoring. The early instruments available to volcano observers were simple by modern standards. Seismographs could detect the shaking of the ground, providing warning of the earthquakes that often accompanied volcanic activity. Thermometers could measure temperature changes in hot springs and fumaroles, tracking the heat output of the volcanic system. Visual observation remained important, the careful watching of smoke and steam, of changes in the crater, of any signs of lava or increased activity. Photography, as it developed through the 19th century, added a new tool to the observer's kit. Where before visual records had depended on the skill of artists like Fabris, now cameras could capture volcanic phenomena with mechanical accuracy. The photographs could be compared over time, changes documented with precision that drawings could not match. The archive of images that accumulated at volcano observatories became a resource for understanding long-term patterns, for comparing different eruptions, for training new generations of observers. The presence of the observatory shifted the relationship between scientists and the volcano. Rather than visitors who came and went, the observatory staff became residents, people who knew the mountain through years of daily acquaintance. They developed the kind of familiarity that Hamilton had reached through his persistent visits, but settled it into routine, making it a permanent feature rather than a personal achievement. The volcano was no longer something to be visited, but something to be lived with, watched, and gradually understood. The data that accumulated at the observatory took on value greater than any individual observation. Patterns gathered in the long records, seasonal variations, multi-year cycles, precursors to eruptions that appeared in the data, but might be missed by intermittent visitors. The continuous observation gradually shifted volcanic study from a collection of dramatic incidents into a science of process, of change over time, of the slow workings of a system that occasionally produced spectacular events. The routine of the Vesuvius Observatory established patterns that would be followed by volcano observatories around the world. Each day, observers would record the state of the volcano, the quantity and color of smoke rising from the crater, the presence or absence of visible activity, any unusual sounds or smells. Instruments would be read and their values logged, creating continuous records that could be compared over time. Any changes from normal conditions would be noted and investigated, with additional observations conducted if warranted. The value of this routine lay in its consistency. By making the same observations in the same way, day after day, the observers built a baseline against which changes could be detected. A slight increase in seismic activity, a shift in the composition of volcanic gases, a small change in the shape of the crater. These subtle signals might be missed by intermittent visitors, but would stand out in the continuous record as departures from normal behavior. The routine was not exciting, but it carried the work forward. The staff of early volcano observatories often lived at their posts, maintaining the continuous presence that the work required. They developed intimate knowledge of their volcanoes, learning to recognize the subtle signs that distinguished ordinary background activity from the precursors of eruptions. This accumulated familiarity, passed from one generation of observers to the next, became part of the institutional knowledge of the observatories, as valuable in its way as the instrumental records they maintained. The preparation of thin sections for microscopic examination requires considerable skill. A slice of rock must be cut and ground until it is thin enough for light to pass through, typically about 30 micrometers. Thin enough that the rock becomes essentially transparent. The slice is then mounted on a glass slide and polished until its surface is optically smooth. The process can take hours for a single section, and the result is a window into the rock's internal structure that reveals details invisible at larger scales. Under the microscope, volcanic rocks reveal their histories. The crystals that make up the rock show their shapes and relationships, the way they grew and interacted as the magma cooled. Some crystals are large and well formed, indicating slow cooling that gave them time to develop. Others are small and irregular, indicating rapid cooling that froze the rock before crystals could fully form. Still others show complex zoning, layers of different composition that record changing conditions during their growth. The optical properties of minerals, the way they interact with polarized light, allow their identification with considerable precision. Different minerals show different colors and patterns when viewed through crossed polarizers, their crystal structures interacting with light in characteristic ways. A trained petrographer can identify dozens of minerals by their optical properties alone, reading the composition of a rock from the colors and patterns visible in thin section. The minerals that form in volcanic systems hold information about conditions that cannot be directly observed. Olivine, the green mineral common in basaltic rocks, crystallizes at temperatures exceeding 1,000 degrees Celsius, its chemistry recording the composition and temperature of the magma from which it formed. Quartz, common in more silica-rich volcanic rocks, requires different conditions, its presence indicating a different evolutionary path for the magma. Each mineral carries a quiet message from the depths, its properties holding the conditions of its formation. The study of these minerals has revealed much about the processes occurring in magma chambers beneath volcanoes. Crystals often show zoning, concentric layers of slightly different composition that record changing conditions during their growth. By examining these zones, scientists can gradually piece together the history of the magma, the episodes of new magma injection, the changes in temperature and pressure as the chamber developed. A single crystal, millimeters in size, can hold a record spanning thousands of years of volcanic activity. The temperatures and pressures at which specific minerals are stable have been determined through laboratory experiments, melting rocks under controlled conditions and observing what minerals form as they cool. These experiments provide calibrations that allow the conditions in natural systems to be estimated from the minerals present. The agreement between experimental results and natural observations gives confidence that the conditions inferred from volcanic rocks are meaningful, that the minerals are reliable witnesses to the depths from which they came. The different types of volcanoes found across the Earth reflect different conditions of magma formation and ascent. Shield volcanoes, like those of Hawaii, are built from fluid basaltic lavas that flow easily and spread widely, building broad, gently sloping structures. Stratovolcanoes, like Vesuvius or Mount St. Helens, are built from more viscous andesitic or dacitic magmas that tend to explode rather than flow, building steep-sided cones of layered lava and ash. Cinder cones are small, simple volcanoes built from fragments ejected in explosive eruptions. Each type tells of different conditions in the magma that fed it. The viscosity of magma, its resistance to flow, depends primarily on its silica content and temperature. Basaltic magmas, with relatively low silica, are fluid and flow easily. Rhyolitic magmas, rich in silica, are viscous and tend to clog their vents, building pressure until explosive eruptions occur. The intermediate magmas produce intermediate behaviors, sometimes flowing smoothly, sometimes erupting explosively, depending on gas content and other factors. The depth at which magma forms shapes its composition. Basaltic magmas typically form at relatively shallow depths in the mantle, where the rock melts partially to produce a liquid rich in iron and magnesium. Andesitic and more silica-rich magmas often form when basaltic magma interacts with continental crust, melting crustal rocks and incorporating their more silica-rich compositions. The chemistry of a volcanic rock thus tells of the processes that created its parent magma, holding evidence of conditions deep below the surface. The study of volcanic rocks under the microscope opened a new window into the depths of the Earth, where earlier observers had examined rocks with the naked eye, noting color and texture and overall composition. The microscope revealed details that were invisible at larger scales. Thin sections of rock, sliced so thin that light could pass through them, showed the individual crystals that made up volcanic material, their shapes and arrangements and relationships to one another. The science of petrology, the study of rocks, developed steadily in the 19th century as microscopic techniques improved. Scientists learned to identify minerals by their optical properties, the way they interacted with polarized light, the colors and patterns they displayed under the microscope. Different minerals formed under different conditions, their presence in a rock telling of the temperatures and pressures that had prevailed when the rock crystallized. The volcanic rocks brought up from depth carried information about the places they had come from, held in the minerals they contained. The crystals in volcanic rocks told stories of their formation. Large crystals had cooled slowly deep beneath the surface where temperatures dropped gradually. Small crystals had cooled quickly near the surface where temperatures dropped rapidly. Glassy volcanic rock had cooled so quickly that crystals had no time to form at all, the molten material settling into an amorphous solid. The texture of a rock, the size and arrangement of its crystals, offered evidence of its thermal history, the journey it had taken from melt to solid. Certain minerals could only form under specific conditions. Olivine, a green mineral common in basaltic rocks, formed at high temperatures and relatively shallow depths. Garnet, a dense mineral often found in metamorphic rocks, formed at greater depths and pressures. By identifying the minerals present in a volcanic rock, petrologists could estimate the conditions under which the rock had formed, gradually building a picture of the environments deep within the earth where such conditions prevailed. The chemical analysis of volcanic rocks added another dimension to this understanding. Different volcanoes produced lavas of different compositions, some rich in silica and others poor in it, some containing certain trace elements and others lacking them. These chemical variations pointed to differences in the source regions, the places deep within the earth where the magmas originated. A volcano was not just a vent in the surface, but the surface expression of a deep system, a column of heat and melt that extended far below what anyone could see. The connection between surface volcanoes and deep magma chambers became clearer as studies accumulated. The magma that fed an eruption had to come from somewhere. It gathered in chambers below the volcano, sometimes for years or decades before an eruption brought it to the surface. The chemistry and mineralogy of the erupted material provided clues about these chambers, their depths and sizes and temperatures, though the chambers themselves remained hidden from direct observation. The distribution of volcanoes across the Earth's surface seemed at first to be random, or at least to follow patterns that were not immediately explicable. Volcanoes clustered along certain coastlines, formed chains across certain ocean regions, appeared on isolated islands far from any continent. Some areas had many volcanoes while others had none at all. This distribution invited explanation, and the search for that explanation would eventually reshape understanding of the Earth. Early observations noted that volcanoes seemed to concentrate along the edges of continents, particularly around the Pacific Ocean, where the so-called Ring of Fire included most of the world's most active volcanoes. Island chains like Hawaii and the Galapagos suggested that oceanic regions too had their volcanic systems, though these seemed to operate differently from the coastal volcanoes. The patterns were clear, but the causes remained unclear. The idea of continental drift, proposed in various forms during the early 20th century, offered a possible explanation. If continents could move, then the edges where they collided or separated might be places of particular geological activity, including volcanism. But the mechanism for continental movement was unclear, and the idea remained unsettled, accepted by some geologists but rejected by many others who could not see how such massive structures could possibly move. The mapping of the ocean floor, which accelerated dramatically after World War II, brought to light features that called for new explanations. Mid-ocean ridges, vast underwater mountain ranges running through the centers of ocean basins, turned out to be sites of volcanic activity and seafloor spreading. Deep ocean trenches, where the seafloor plunged steeply downward, marked places where oceanic crust was being subducted, drawn down into the Earth's interior. The pattern of volcanoes gradually made more sense. They concentrated along ridges where new crust was forming and along trenches where old crust was being destroyed. The drawing together of these observations into the theory of plate tectonics occurred primarily in the 1960s, though it built on decades of earlier work. The Earth's surface was not a single continuous shell, but a mosaic of rigid plates that moves slowly over the hotter, more fluid layers beneath. Where plates spread apart, magma rose to fill the gap, creating new crust and volcanic activity at mid-ocean ridges. Where plates converged, one plate descended beneath the other, creating subduction zones marked by deep trenches and chains of volcanoes. Where plates slid past each other, earthquakes were common, but volcanoes rare. The theory of plate tectonics offered the framework that had been missing, the organizing principle that drew the scattered observations of volcanic activity into a coherent global picture. Volcanoes were not random occurrences, but expressions of deep planetary processes, the surface manifestations of movements that affected the entire Earth. The heat that lay behind these movements came from the interior, from the decay of radioactive elements, and from the original heat of the Earth's formation, rising slowly toward the surface and carrying the plates in their endless slow drift. The evidence that gradually convinced scientists of plate tectonics came from many sources, accumulated over decades before the theory was finally accepted. The fit of the continents, particularly Africa and South America, had been noticed for centuries, but without a mechanism to explain continental movement, the observation remained a curiosity. The distribution of fossils, with identical species found on continents now separated by oceans, suggested past connections, but could be explained by other means. The pattern of earthquakes and volcanoes hinted at an underlying structure, but did not yet reveal what that structure might be. The most telling evidence came from the ocean floor, which had been largely unknown until the mid-20th century. Surveys conducted for military purposes during and after World War II revealed unexpected features: a global system of mid-ocean ridges, deep trenches along certain coastlines, a relatively uniform thickness of oceanic crust compared to the highly variable thickness of continental crust. The ocean floor was not ancient, as had been assumed, but geologically young, continuously created at ridges and slowly recycled at trenches. The discovery of magnetic striping on the ocean floor brought the picture together. As new crust forms at mid-ocean ridges, it records the orientation of the Earth's magnetic field at the time of its formation. The magnetic field reverses periodically, and these reversals are recorded in the rocks of the ocean floor as parallel stripes of alternating magnetic polarity. The symmetry of these stripes on either side of mid-ocean ridges showed that new crust was indeed forming at the ridges and moving away in both directions, providing the mechanism that previous theories had lacked. Far below, beneath the silence of the deep ocean, this slow forming and moving has continued without pause for as long as the planet has existed. The subduction zones, where one plate descends beneath another, are among the most geologically active regions on Earth. The descending plate carries water and sediment into the mantle, where rising temperatures release the water into the overlying rocks. This water lowers the melting point of the mantle material, generating the magmas that feed the explosive volcanoes of island arcs and continental margins. The process is slow. The descent measured in centimeters per year, but over millions of years it has built the volcanic mountain ranges that rim the Pacific Ocean. The earthquakes that accompany subduction are among the largest and most destructive on Earth. The locked zone where the two plates meet accumulates stress over decades or centuries, then releases it suddenly in great earthquakes that can generate tsunamis and affect coastal areas across great distances. The 2004 Indian Ocean earthquake and the 2011 Tohoku earthquake in Japan were both subduction zone events. Their magnitude and reach reflected the vast energies involved in the descent of oceanic plates beneath continental margins, The volcanic arcs that parallel subduction zones display a characteristic chemistry that reflects their origin. The magmas produced by subduction-related melting are typically andesitic to dacitic in composition, richer in silica than the basalts of mid-ocean ridges, more viscous and more prone to explosive eruption. The dramatic volcanoes of the Ring of Fire owe their explosive character to the processes occurring deep in the subduction zones that feed them. The release of water from descending slabs triggers melting that eventually reaches the surface in dramatic and sometimes destructive eruptions. The mid-ocean ridges that wind through the world's ocean basins are the longest mountain ranges on Earth, though most of their extent lies hidden beneath miles of water. At these ridges, tectonic plates pull apart and magma rises from the mantle to fill the gap, creating new oceanic crust in a process that has been continuing for billions of years. The ridges are not continuous, but broken into segments offset by transform faults, creating a pattern that reflects the complex geometry of plate motions. The volcanism at mid-ocean ridges is unlike that at subduction zones. The magmas are basaltic, fluid, and relatively quiet in their eruption. There are no explosive events, no towering ash columns, no pyroclastic flows. Instead, lava wells up and flows out across the sea floor, building pillow-shaped formations as it cools in contact with cold seawater. The eruptions happen constantly but invisibly, unseen beneath the waters of the deep ocean, creating new crust at rates of a few centimeters per year. The discovery that new crust was being created at mid-ocean ridges was one of the key insights that led to the acceptance of plate tectonics. If new crust was continuously being created, then either the Earth was expanding or old crust was being recycled somewhere else. The recognition that crust was being subducted at ocean trenches completed the picture, revealing a planet whose surface was in constant slow motion, recycling its outer layers over timescales measured in hundreds of millions of years. The hotspots that produce volcanic island chains like Hawaii represent yet another type of volcanic activity, one that does not fit neatly into the plate boundary framework. Hotspots are believed to originate from plumes of unusually hot material rising from deep in the mantle, perhaps from as deep as the boundary between the mantle and the core. As plates move over these stationary plumes, they create chains of volcanoes that record the direction and rate of plate motion. The Hawaiian Islands provide the classic example of a hotspot track. The active volcanoes of the Big Island sit over the current position of the hotspot, while the older islands to the northwest represent earlier positions of the plate over the same heat source. The ages of the islands increase regularly with distance from the current hotspot. Together, they offer a remarkably clear record of Pacific plate motion over tens of millions of years. The plumes that create hotspots bring material from the deep mantle to the surface, offering samples of Earth's interior that plate boundary volcanism does not provide. The chemistry of hotspot lavas differs subtly from that of mid-ocean ridge basalts, reflecting the different source regions and the different paths to the surface. These differences have provided evidence about the composition and structure of the deep mantle, regions that cannot be sampled directly, but that gradually reveal themselves through the volcanic products they send to the surface. The convection currents that drive plate motion operate on timescales almost impossible to grasp. The mantle is solid rock, yet it flows, moving at rates measured in centimeters per year, carrying the plates on its surface like objects floating on a very slow river. A single convection cycle, from surface to depth and back again, takes hundreds of millions of years to complete. The patterns we see at the surface The distribution of plates and the locations of their boundaries are snapshots of a process that has been operating since the Earth formed. It will continue until the planet's internal heat is exhausted. And still, the planet moves beneath it all, slowly enough that no human life could ever notice the motion directly. The slow movement of plates has rearranged the surface of the Earth countless times over geological history. Continents that are now separate were once joined. Oceans that now exist will eventually close as plates converge. Mountain ranges rise where plates collide and erode away over tens of millions of years. Ocean basins open as continents rift apart, then close as the rift evolves into a subduction zone. The map of the world is never static, always shifting, though so slowly that human civilizations rise and fall without noticing the motion. The history of these movements is recorded in the rocks of the continents. The ancient mountains of Scotland were once connected to similar rocks in North America, before the Atlantic Ocean opened between them. The Himalayas continue to rise as India pushes into Asia, a collision that has been ongoing for tens of millions of years. The geological record is a history written in stone, holding the movements of plates over billions of years, telling of worlds quite different from the one we know. And the space around you stays unchanged, while these slow continental drifts move on, far below. The instruments that modern volcanologists use to monitor their subjects are far more sophisticated than anything Hamilton or the early observatory staff could have imagined. Seismometers sensitive enough to detect the smallest tremors, the movements of magma deep below the surface, the cracking of rock as pressure builds toward an eruption, tilt meters that measure the swelling of a volcano as magma accumulates beneath it, changes of a few microradians that would be invisible to the eye, but that signal significant movement of material underground. Gas sensors that sample the emissions from volcanic vents, tracking changes in composition that can indicate rising magma or impending activity. The instruments do their work without pause, through the long quiet of the night and the steady warmth of the day. The data accumulates while the watchers sleep and while they wake. The seismic monitoring of volcanoes has become particularly nuanced. Different types of seismic signals correspond to different volcanic processes. The brittle fracturing of rock as magma forces its way upward. The resonance of fluid moving through underground conduits. The harmonic tremors that often precede eruptions. Scientists have learned to read these signals, distinguishing between the background noise of a quiet volcano and the signs of increasing activity. The seismographs write their traces continuously, day and night. Their records can be examined later for patterns invisible to casual observation. The swelling of a volcano as magma accumulates beneath it can be detected by instruments even when no other signs of activity are apparent. Tilt meters and GPS receivers track the position of the volcano's surface with precision measured in millimeters, detecting inflation that might signal an approaching eruption. The measurements are made continuously, building records that show the breathing of the volcano over time, the slow accumulation of pressure followed by release, the rhythms of a system that operates on timescales from hours to years. The gases that volcanoes emit carry information about the processes occurring below: sulfur dioxide, carbon dioxide, hydrogen sulfide, water vapor. Each gas has its own significance, its own story to tell about temperatures and compositions and depths. As magma rises and depressurizes, gases that were dissolved in it come out of solution, escaping through vents and fissures to the atmosphere. The changing ratio of different gases can indicate changes in the magma, new injections of material from depth, the approach of an eruption. Satellite observation has added a global dimension to volcano monitoring. Thermal sensors can detect the heat signatures of volcanoes from orbit, identifying changes in surface temperature that might indicate increased activity. Radar instruments can measure the swelling and deflation of volcanic edifices from space, tracking changes over entire regions simultaneously. Cameras capture images of eruption plumes, tracking their height and spread, monitoring the distribution of ash that can affect aviation and climate. The combination of all these instruments creates a picture of volcanic activity more detailed than anything previously possible. A modern volcano observatory draws together data from dozens of sensors, building a comprehensive portrait of the volcano's state that can be updated continuously. When changes occur, when seismic activity increases or the ground begins to swell, the instruments register it and scientists can respond, issuing warnings if necessary, adjusting their attention to the changing situation. The watching itself is mostly uneventful. Most days, the data shows what the data has shown the day before and the day before that. The bringing together of data from multiple instruments at modern volcano observatories creates a picture more comprehensive than any single measurement could provide. A seismometer detects the brittle fracturing of rock as magma forces its way upward, but cannot distinguish between a minor adjustment and the beginning of an eruption. A tilt meter records the swelling of the volcano as pressure builds, but cannot indicate where that pressure will be released. Gas sensors show changes in the composition of volcanic emissions, but cannot foretell when those changes will lead to eruptive activity. Only by combining all these data streams can observers develop a full picture of the volcano state. The interpretation of volcanic monitoring data calls for both scientific understanding and practical experience. The theoretical basis for each measurement is well established. Seismic waves are generated by rock fracture. Ground deformation reflects changes in subsurface pressure. Gas compositions reflect conditions in the magma. But the application of these principles to specific volcanoes requires knowledge of how each volcano behaves, what patterns of activity are normal for it, what departures from normal warrant attention. The warnings that observatories issue rest on probabilistic assessments rather than certainties. A particular combination of signals might suggest a 70% probability of eruption within the next week, or a 10% probability of a major eruption within the next month. These probabilities are the best that can be reached given the complexity of volcanic systems and the limitations of current understanding. The aim is not to predict eruptions with certainty, but to give decision makers the information they need to protect lives and property. The monitoring of volcanic gases has become increasingly refined, with sensors capable of detecting changes in composition that might signal rising magma. Sulfur dioxide is particularly useful because it is released from magma as it rises and depressurizes, its presence at the surface indicating that fresh magma is approaching. Carbon dioxide, which is less soluble in magma, can be released from greater depths, providing earlier word of magma movement. The ratio of different gases tracked over time creates a chemical portrait of the volcanic system. It complements the physical measurements from seismometers and tilt meters. The gases released by volcanoes also affect the atmosphere and climate. Large eruptions can inject sulfur dioxide into the stratosphere, where it forms sulfate aerosols that reflect sunlight and cool the Earth's surface. The eruption of Mount Pinatubo in 1991 lowered global temperatures by about 0.5 degrees Celsius for a year or more. Even larger eruptions in the geological past have caused more dramatic climate effects, some possibly contributing to mass extinctions. Volcanic gases are thus both tools for monitoring and agents of global change. The collection of volcanic gas samples requires approaching active vents, often in conditions of considerable personal risk. Scientists wearing protective equipment and carrying specialized sampling equipment climb to crater rims and approach fumaroles where gases emerge at high temperatures. The samples they collect are analyzed in laboratories, their compositions determined with precision that field instruments cannot match. This direct sampling complements the continuous monitoring provided by automated sensors, offering detailed data at specific moments to calibrate the ongoing measurements. The satellite observation of volcanoes has shifted the study of volcanic activity onto a global scale. Thermal sensors can detect the heat signatures of lava lakes and active vents from orbit, monitoring activity at remote volcanoes that would otherwise be unobserved. Radar instruments can measure changes in the shape of volcanic edifices with millimeter precision, detecting the swelling and deflation that accompanies magma movement. Cameras capture images of eruption plumes, tracking their height and extent, providing data for aviation safety and atmospheric modeling. The global view provided by satellites reveals patterns that ground-based observation cannot detect. The distribution of active volcanoes, their state of activity at any given moment, the movements of ash clouds across continents and oceans, all of this becomes visible from orbit. The satellite data are combined with ground-based measurements to build comprehensive pictures of volcanic activity worldwide, allowing scientists to study volcanoes as elements of a global system rather than as isolated phenomena. The application of satellite technology to volcano monitoring has been particularly valuable for remote volcanoes in sparsely populated regions. Volcanoes in Alaska, Kamchatka, and the islands of Indonesia, far from major population centers and difficult to access on the ground, can be monitored continuously from space. When activity increases, ground-based resources can be deployed more effectively, guided by the overview that satellites provide. The combination of space-based and ground-based monitoring creates a system more capable than either approach alone. The timing of volcanic eruptions remains one of the most difficult problems in Earth science. Unlike earthquakes, which release accumulated stress in sudden ruptures, volcanic eruptions involve the movement of fluid material through complex pathways, processes that can stall or accelerate in ways that are not always foreseeable. An increase in seismic activity might herald an imminent eruption or might subside without any surface activity at all. The signs that volcanologists watch for are necessary but not sufficient conditions for eruption. Their presence indicates elevated risk, not certainty. The historical record provides context for interpreting current observations. Volcanoes that have erupted frequently in the past are more likely to erupt again than those with no historical activity. The intervals between past eruptions suggest the timescales on which future eruptions might occur, though individual intervals vary widely and cannot be used for precise prediction. The pattern of activity at a particular volcano, its characteristic style of eruption, and the typical signs that precede activity becomes known through accumulated observation and becomes the basis for interpreting new signals. The uncertainty that surrounds volcanic prediction is not a failure of science, but a reflection of the complexity of volcanic systems. The factors that determine whether rising magma will reach the surface or stall in the crust, whether an eruption will be explosive or effusive, whether it will last hours or months. These depend on details of magma composition, gas content, conduit geometry, and stress state that cannot be fully known from surface observations. The aim of volcano monitoring is not to predict eruptions with certainty, but to offer the best possible assessment of risk given the available information. The supervolcanic systems that exist in several locations around the world represent potential hazards on a scale that dwarfs ordinary volcanic eruptions. These systems, including Yellowstone in the United States, Taupo in New Zealand, and several others, are capable of eruptions thousands of times larger than the most destructive historical events. Such eruptions have occurred in the geological past, leaving calderas tens of kilometers across and ash deposits covering entire continents. The monitoring of supervolcanic systems brings particular challenges. The magma chambers that feed these systems lie deep beneath the surface, their behavior difficult to interpret from surface observations. The timescales on which they operate are long, even by geological standards. The intervals between major eruptions are measured in hundreds of thousands of years, determining whether activity at such a system represents the approach of a catastrophic eruption or merely the normal fluctuations of a restless but stable system lies beyond current scientific capability. The probability of a supervolcanic eruption in any human lifetime is low, but the consequences of such an event would be considerable, and the study of these systems remains a quiet and ongoing concern. The ash from a Yellowstone super-eruption could blanket much of North America, affecting agriculture and infrastructure across the continent. The climate effects could last for years, reaching the entire planet. The study of supervolcanic systems is thus not merely academic. It has implications for understanding risks that, while unlikely, are potentially civilization-shaping. And you remain here, settled in the quiet, while these distant possibilities drift far beyond reach. The Kola Superdeep Borehole project began in 1970 with ambitious aims to penetrate deep into the Earth's crust, to reach the boundary between the crust and the underlying mantle, to learn what conditions prevailed at depths that had never been directly sampled. The project continued for over 2 decades, drilling through rock that became progressively hotter and more difficult to penetrate, facing challenges that pressed the limits of available technology. The drilling encountered temperatures that exceeded predictions. At 12 kilometers depth, where the hole finally stopped, temperatures approached 180 degrees Celsius, hot enough that conventional drilling equipment could not function effectively. The rock at this depth behaved differently from rock at the surface, more plastic and prone to closing around the drill, calling for new techniques to maintain the hole. The physical conditions of the deep crust proved more extreme than models had suggested. The core samples brought up from the borehole offered direct evidence of crustal conditions that could previously only be inferred. The rocks showed the effects of the pressures and temperatures they had experienced, their minerals holding the conditions of their environment. Water was found at unexpected depths, apparently held in the rocks for billions of years, its presence gently challenging assumptions about the dry lower crust. Each sample was a quiet message from a place that humans could never visit, information held in minerals and textures that scientists learned to read. The heat that flows from the Earth's interior to the surface is measured at many locations around the world, providing data on how energy moves through the planet. Heat flow varies from place to place, higher in volcanically active regions and along mid-ocean ridges, lower in the old, stable interiors of continents. These variations reflect the underlying structure of the Earth, the distribution of heat sources, and the efficiency of different materials in conducting heat toward the surface. The total heat flowing out of the Earth amounts to about 44 terawatts, a continuous output that has been maintained for billions of years. About half of this heat comes from the decay of radioactive elements, primarily uranium, thorium, and potassium, distributed through the crust and mantle. The other half is primordial heat, the residual warmth from the Earth's formation, still slowly dissipating into space after 4.5 billion years. This heat budget shapes the geological activity of the planet, supporting the movements of plates and the eruptions of volcanoes. The cooling of the Earth is so slow that it has barely progressed over geological time. The planet loses heat from its surface, but the interior remains hot, the insulating effect of the overlying rock, slowing the escape of energy. At current rates, the Earth will remain geologically active for billions of years to come, its volcanoes still erupting, its plates still moving, its interior still providing the energy that lies behind the processes that shape the surface. The structure of the Earth beneath the crust has been revealed primarily through seismology, the study of how seismic waves travel through the planet. When an earthquake occurs, it generates waves that propagate through the Earth, their paths bent and their speeds altered by the materials they encounter. By recording these waves at stations around the world and examining how they have been affected by their journey, seismologists can build images of the Earth's interior with remarkable detail. The mantle, the thick layer between the crust and the core, proves to be more complex than the early models suggested. It is not uniform, but varies in composition and temperature with depth and location. The upper mantle is relatively cool and rigid, forming part of the tectonic plates along with the crust above it. The lower mantle is hotter and more plastic, flowing slowly over geological time. The boundary between the mantle and the core, marked by dramatic changes in seismic wave behavior, remains one of the most mysterious regions of the planet. The core itself is divided into two parts: a liquid outer core of iron and nickel, and a solid inner core at the very center. The liquid outer core is in constant motion, driven by the combination of heat from the inner core and the rotation of the Earth. And this motion generates the magnetic field that shields the surface from harmful solar radiation. The inner core, despite temperatures exceeding those at the surface of the Sun, remains solid because of the immense pressure at the planet's center. The lava flows that descend from volcanic vents vary widely in their behavior, depending on their composition and temperature. Basaltic lavas, hot and fluid, can flow for many kilometers, their progress slow enough that people can usually move out of their way, but fast enough that buildings and infrastructure in their path will be lost. More silica-rich lavas are cooler and more viscous, forming thick, slow-moving masses that may travel only short distances from their vents. The distinction matters for hazard assessment, shaping which areas are at risk and how much time is available for response. The surfaces of lava flows take different forms depending on how they cool. Pahoho, a Hawaiian term, describes flows with smooth, ropey surfaces that form when fluid lava flows slowly, and its surface skin wrinkles as it moves. Ah, another Hawaiian term, describes flows with rough, jagged surfaces that form when more viscous lava moves quickly enough to break its cooling skin into sharp fragments. The two types can grade into each other as conditions change during a single flow, the surface texture holding the history of the flow's movement. The solidification of a lava flow is not instantaneous, but proceeds gradually from the outside in. The surface cools first, forming a crust that insulates the still liquid interior. Beneath this crust, molten lava can continue to flow, sometimes draining away, and leaving tubes that persist after the flow has solidified. These lava tubes can extend for many kilometers, their insulating effect allowing lava to travel far from its source while remaining fluid. The landscapes produced by volcanic eruptions are complex, the result of processes that continue long after the eruption itself has ended. The ash that volcanoes eject can travel far from its source, carried by winds across continents and sometimes around the world. Fine ash particles can remain suspended in the atmosphere for weeks, affecting air quality hundreds of kilometers from the eruption. Heavier ash falls closer to the volcano, accumulating in layers that can collapse roofs, contaminate water supplies, and bury agricultural land. The reach of a volcanic eruption extends far beyond the immediate vicinity of the volcano itself. The composition of volcanic ash varies with the type of volcano and the nature of the eruption. Basaltic ash tends to be dark and dense, while ash from more silica-rich eruptions is lighter in color and often more abrasive. The shape of ash particles, typically angular and sharp-edged, makes them particularly difficult for machinery, aircraft engines, and respiratory systems. The same properties that make ash hazardous also make it useful for geological studies, its composition providing information about the magma from which it originated. The deposition of volcanic ash creates records that can be read by geologists studying past eruptions. Ash layers preserved in sediments, ice cores, and marine deposits serve as time markers, their distinctive compositions allowing them to be correlated across wide areas. These layers provide evidence of eruptions that occurred before recorded history, allowing scientists to extend the record of volcanic activity back thousands or millions of years. The ash that falls from an eruption today will become part of this geological record, a quiet message to future generations about events that are now current. The relationship between volcanic activity and climate has been recognized since the earliest scientific observations. Benjamin Franklin, observing the unusually cold summer of 1783 in Paris, considered that the volcanic haze from the Laki eruption in Iceland might be responsible for the cooling. Modern research has confirmed and quantified this relationship. Large eruptions can inject sulfur dioxide into the stratosphere, where it forms aerosols that reflect sunlight and cool the surface for months or years. The eruption of Tambora in Indonesia in 1815 produced the most pronounced climate effect in recorded history. The following year, 1816, became known as the year without a summer, with frosts in June and July causing crop failures across Europe and North America. The cooling was temporary, lasting only a few years until the volcanic aerosols settled out of the atmosphere. But its effects on agriculture and society were considerable. The connection between volcanic eruptions and climate variability has implications for understanding both past and future climate change. The longer-term effects of volcanic activity on climate are more complex. Over geological time, volcanic emissions of carbon dioxide contribute to greenhouse warming, while volcanic aerosols contribute to cooling. The balance depends on the frequency and intensity of eruptions, which varies considerably over time. During periods of intense volcanic activity, the climate effects can be significant. During quiet periods, other factors take precedence. The volcanic influence on climate is one thread in a complex tapestry of interacting processes that shape the conditions at Earth's surface. The record of volcanic activity preserved in ice cores from Greenland and Antarctica extends the history of eruptions far beyond the reach of written records. When volcanoes erupt, they inject sulfur compounds into the atmosphere that eventually settle onto polar ice sheets, where they are preserved in annual layers that can be dated precisely. By examining these layers, scientists can identify eruptions that occurred thousands of years ago, estimating their magnitude from the amount of sulfur deposited. This ice core record has revealed eruptions that were unknown from historical sources, events that occurred before writing or in regions without literate observers. Some of these eruptions were enormous, larger than anything in recorded history. Their effects on climate potentially significant for years. The identification of these events helps calibrate the frequency of large eruptions, providing context for considering the risks that volcanic activity poses today. The combination of ice core records, geological surveys, and historical accounts builds a comprehensive picture of volcanic activity over time. This picture shows that large eruptions are not rare, that events capable of significant climate effect occur every few decades or centuries. The quiet periods between major eruptions can give a false sense of security. The record shows that such periods always end, that the forces that lie behind volcanic activity continue to operate even when no eruptions are visible at the surface. The recovery of landscapes after volcanic eruptions follows patterns that ecologists have studied at sites around the world. The initial disturbance can be total, all vegetation gone, soils buried or stripped away, the terrain rendered apparently lifeless. Yet recovery begins almost immediately, with pioneer species settling on the new surfaces, their growth gradually transforming bare rock and ash into substrates that can support more complex communities. The process is slow, taking decades or centuries to restore mature ecosystems, but it shows the resilience of life in the face of major disturbance. The volcanic soils that develop on weathered lava and ash are often remarkably fertile. The minerals released as volcanic rocks break down provide nutrients that plants require, making volcanic regions agriculturally productive despite the hazards they pose. The slopes of Vesuvius, Etna, and other famous volcanoes support vineyards and orchards, their fertility drawing populations into areas that periodic eruptions will affect. The agricultural benefits of volcanic soils have always sat alongside the risks of volcanic activity, a balance that human societies have repeatedly chosen to accept. The hot springs and other geothermal features that accompany volcanic activity support unique ecosystems adapted to extreme conditions. Thermophilic bacteria thrive in waters too hot for most life, their metabolisms drawn from the chemical energy that volcanic systems provide. These organisms represent some of the most ancient forms of life on Earth, their heat-loving ancestors possibly among the first living things to evolve. The volcanic systems that seem so hostile to life may in fact have been its cradle, providing the energy and chemistry that allowed life to begin. The long history of human settlement near volcanoes reflects a quiet calculation that has been made countless times. The benefits of volcanic regions often outweigh their risks. The fertile soils that develop on weathered volcanic materials support productive agriculture. The geothermal resources provide energy. The mineral deposits offer economic opportunity. The dramatic landscapes draw visitors. Against these benefits, the prospect of eruption seems distant, a possibility that may not arrive for generations, that can perhaps be managed through monitoring and preparation. The communities that live in volcanic regions develop their own relationships with the mountains that dominate their landscapes. Children grow up with volcanoes as familiar presences, their shapes visible from windows, their activity a topic of casual conversation. The rumbling and steaming that would unsettle visitors become background, part of the normal texture of life. This familiarity can lead to complacency, making it difficult to convince people to evacuate when warnings are issued, but it also reflects a reasonable assessment of risks that are real, but, most of the time, manageable. The volcanic landscapes themselves become part of cultural identity. The shapes of volcanic mountains appear in art and literature, in religious symbolism and national imagery. Mount Fuji is inseparable from Japanese identity. Vesuvius defines the Bay of Naples. The volcanoes of the Cascade Range shape the character of the Pacific Northwest. These mountains are not merely geological features, but cultural landmarks. Their presence woven into the fabric of the societies that live in their shadows. The cultural responses to volcanic activity have varied across societies and times. In many volcanic regions, the mountains that hold the potential for harm are also objects of respect, their power inviting awe and care. The ancient Greeks placed the forge of Hephaestus beneath Etna. The Hawaiians understood their volcanoes as manifestations of the goddess Pele. These interpretations did not prevent people from observing volcanic phenomena carefully. Rather, they provided frameworks within which observations could be understood and passed on. The scientific study of volcanoes has not entirely replaced these cultural understandings, but coexists with them. In Hawaii, respect for Pele remains strong, even among people who also understand the geological processes that produce eruptions. In Japan, sacred mountains like Fuji are understood both as spiritual sites and as volcanoes, with the potential for future activity. The different frameworks address different human needs. The scientific framework offers prediction and protection. The cultural framework offers meaning and connection. The communication of volcanic hazards to populations at risk calls for sensitivity to these cultural dimensions. Warnings framed purely in scientific terms may not resonate with communities that understand their volcanoes through different lenses. Effective communication often involves collaboration between scientists and local leaders, drawing scientific information together with local knowledge and cultural understanding. The aim is not to replace traditional understandings, but to weave them with scientific monitoring in ways that protect lives while respecting the values of the communities involved. The volcanic activity of other planets and moons in our solar system provides context for understanding Earth's volcanism. Mars bears enormous shield volcanoes, including Olympus Mons, the largest volcano in the solar system, built by processes similar to those that create Hawaiian volcanoes, but operating on a larger scale. Venus shows evidence of widespread volcanic activity, its surface dominated by volcanic landforms. Io, a moon of Jupiter, is the most volcanically active body known, its surface continually renewed by eruptions driven by tidal heating from Jupiter's immense gravitational pull. The study of volcanic features on other worlds has been conducted primarily through remote sensing, using spacecraft to image and analyze surfaces that humans have not yet visited. The comparison of these features with terrestrial volcanoes helps scientists understand the range of volcanic processes and the factors that shape them. The similarities reveal fundamental physics and chemistry that operate throughout the solar system. The differences reveal the influence of factors like gravity, atmospheric pressure, and heat source that vary from world to world. The exploration of volcanic systems beyond Earth may eventually extend to direct investigation. Future missions to Mars might examine its ancient volcanoes for evidence of past conditions, possibly including signs of extinct or extant life. The active volcanoes of Io represent extreme conditions that test understanding of volcanic processes. The volcanic systems of other worlds are quiet laboratories for understanding the principles that also shape Earth's volcanism, extending the range of conditions that can be studied and refining the theories that explain them. The geothermal systems that accompany volcanic activity have practical as well as scientific interest. Hot springs and geysers, fumaroles and mud pots, all represent places where Earth's internal heat reaches the surface in accessible form. People have used these resources for thousands of years, bathing in hot springs for relaxation and healing, using geothermal heat for cooking and warmth. Modern technology has extended these uses, drilling wells to access geothermal reservoirs and generating electricity from the steam they produce. The geothermal power plants that operate near volcanic areas tap the same heat that feeds the volcanoes themselves. Water is injected into hot rock formations and returns as steam, which drives turbines to generate electricity. The resource is renewable on human timescales. The heat continually replenished from below, making geothermal power a sustainable alternative to fossil fuels. Iceland generates a substantial fraction of its electricity from geothermal sources, as do regions of the western United States, the Philippines, and other volcanically active areas. The same volcanic heat that supports geothermal systems also creates mineral deposits of economic value. Hot fluids circulating through rock dissolve metals and concentrate them in veins and deposits that can be mined profitably. Gold, silver, copper, and other metals accumulate in volcanic and hydrothermal systems, their presence reflecting the movement of heat and fluid through the crust. The volcanic activity that sometimes shapes the lives of human settlements also creates the mineral wealth on which some of those settlements depend. The wish to reach the Earth's interior directly, to go beyond inference and actually sample what lies below, has guided some remarkable engineering efforts. The deepest holes ever drilled barely scratched the surface of the planet, penetrating only a tiny fraction of the distance to the core. But even these shallow probes have revealed information that surface observation alone could not provide. The Kola super-deep borehole, drilled by Soviet scientists beginning in 1970, reached a depth of more than 12 kilometers, deeper than any other hole ever drilled. The project continued for decades, pressing slowly downward through rock that became progressively hotter and more difficult to penetrate. The temperature increased with depth, as expected, confirming that the Earth's interior is indeed hot, that heat flows constantly from the depths toward the surface. The drilling encountered surprises. The rocks at depth were different from what models had predicted, more fractured and more permeable than expected. Water was found at depths where it had not been anticipated, apparently held in the rock since ancient times. The boundary between different rock layers, which seismic studies had suggested would occur at certain depths, turned out to be more complex and gradual than the seismic data had indicated. Each surprise was a quiet correction to understanding, one that could only come from direct sampling. The borehole confirmed that the crust is thin, a shell of relatively cool, rigid rock floating on hotter layers beneath. At 12 kilometers, the temperatures were already so high that the drilling equipment struggled to function, and the rocks were beginning to behave less like brittle solids and more like the ductile material that characterizes the layers below. The full mantle, the thick layer of hot rock that lies beneath the crust and above the core, remained out of reach, its properties known only through indirect methods. The heat encountered in deep boreholes comes from two sources: the original heat of the Earth's formation, still slowly radiating away after billions of years, and the heat produced by the decay of radioactive elements in the rocks themselves. This heat lies behind the processes that shape the surface, supporting the movement of plates, feeding the volcanoes that bring material from depth, maintaining the slow circulation of the mantle that has continued since the planet formed. The information gathered from deep drilling complements the information gathered from volcanic rocks. The drill holes sample the crust directly, revealing its composition and temperature at depths that cannot be reached any other way. The volcanic rocks sample material that has risen from even greater depths, brought to the surface by the same heat that the boreholes measure. Together, these sources of information build a picture of an Earth that is hot, active, and constantly in motion, even in the depths that remain forever hidden from direct observation. The Earth beneath our feet is not still. The crust on which we stand moves slowly over the deeper layers, carrying continents and oceans on their endless journeys. The mantle below the crust circulates in vast, slow cells, hot material rising from depth and cooler material sinking back down, a pattern of convection driven by the heat that escapes from the core. The core itself, a sphere of iron at the planet's center, generates the magnetic field that shields the surface from solar radiation, its outer layer liquid and in constant motion. These movements are slow beyond human perception. The plates move at rates measured in centimeters per year, the speed of growing fingernails. The circulation of the mantle takes hundreds of millions of years to complete a single cycle. Yet over geological time, these slow movements have rearranged the surface of the planet many times, opening and closing oceans, building and eroding mountain ranges, shifting climates and environments in ways that have shaped the history of life itself. The volcanoes that mark the boundaries of plates are expressions of these deep movements, where plates spread apart at mid-ocean ridges and continental rifts. Magma rises to fill the gap, creating new crust that will eventually be recycled back into the mantle at a subduction zone somewhere else. Where plates converge, water carried down with the subducting slab lowers the melting point of the overlying mantle, generating the magma that feeds the explosive volcanoes of island arcs and continental margins. The surface features that we see are connected to processes that operate throughout the depth of the planet. The minerals that form in the Earth's depths hold the conditions of their formation, the temperatures and pressures and compositions that prevailed when they crystallized. These records, brought to the surface by volcanic eruptions or exposed by erosion, tell of conditions that no human will ever directly observe. Environments of heat and pressure that exist only far below the reach of any drill. The patience required to read these records, to draw out information from crystals and textures and chemical compositions, mirrors the patience of the processes that created them. The heat that lies behind all of these processes continues to escape from the Earth's interior, flowing outward through the crust, emerging at hot springs and volcanic vents, radiating into space from every part of the surface. The planet is slowly cooling, but the cooling is so slow that billions of years have passed, and the interior remains hot, still capable of supporting the movements that shape the surface, still feeding the volcanoes that remind us of the fire below. And so, we come to rest as the surface of the Earth rests upon the layers beneath it. The volcanoes we have visited tonight still stand on their foundations, some quiet for now, others stirring with the heat that continues to rise from the depths. The observatories that watch them still record their data, seismographs tracing their slow movements, sensors sampling their breath, satellites gazing down from orbit at the heat signatures that mark their presence. The depths that we have explored through the eyes of observers and the tools of scientists remain hidden. No one will ever see the mantle directly, will ever touch the outer core, will ever witness the slow circulation of hot rock that lies behind the surface features we know. These depths exist beyond the reach of human senses. known only through inference, through the clues that rise to the surface, through the patient accumulation of observations that gradually build a picture of what lies below. The heat that began this story continues to flow. It rises through the mantle, melts rock into magma, feeds volcanoes that occasionally erupt and then fall quiet again. It warms the hot springs that people have used for millennia, heats the rocks that deep drills encounter, maintains the slow movements of plates that have rearranged the surface of the planet countless times. This heat is ancient, inherited from the formation of the Earth itself, yet it remains capable of shaping the surface for billions of years to come. Let your breathing slow. Let your body grow heavy. The depths of the Earth are far below you, beyond any distance you could travel, beyond any scale you could perceive with your senses alone. Yet they are there, as they have always been there, as they will continue to be there long after the concerns of this day have faded into memory. Think, if you wish, of the heat that rises slowly from below. It moves through rock that seems solid, but flows over geological time, rising and spreading and eventually reaching the surface where it warms springs and feeds volcanoes. This heat asks nothing of you. It continues whether you attend to it or not, a process so slow and so vast that your awareness makes no difference to its progress. You can rest while it continues its ancient work. If you are still awake, you will shortly find another midnight exploration waiting on your screen, or you may choose a playlist to continue your journey through the night. If these stories have brought you peace, please consider liking, subscribing, or sharing your midnight reflections with us. Your support helps our community grow and allows us to reach other fellow explorers wishing to find their rest. The surface of the Earth lies quiet in the darkness, but beneath it the planet continues its slow internal movements. The heat flows upward, the plates drift on their courses. The volcanoes wait for the magma that will someday reach them. None of this requires your attention. None of this needs you to remain awake. Let the weight of stone and the warmth of hidden depths settle into your awareness and then fade. The Earth holds its heat, as it has held it for billions of years, patient and enduring and utterly indifferent to the passing of any single night. The depths that we cannot see continue their work in darkness, as they always have, as they always will. The planet sleeps in its own way, slowly, deeply, for spans of time beyond counting. Good night.